Hola, mis estudiantes de geometría. Here's your lesson for section 6.1, Properties and Attributes of Polygons. Missy McCarthy, Okemos High School, profesor de matemáticas. Profesora de matemáticas. All right, in this lesson you'll learn how to classify polygons based on their side lengths and their angles. And you'll also find and use the measures of interior and exterior angles of a polygon. So let's take a look. What is a polygon? Well, a polygon is nothing more than a closed plane figure bounded by 3 or more line segments. So it has to be two-dimensional because it said it was in a plane, a closed plane, and the figure bounds some region using 3 or more line segments. So what we have here, this figure in red is a polygon. We would name it Polygon A, B, C, D, E. You go in order of the letters A, B, C, D, E. So that's the name of the polygon. And this particular polygon has 5 sides. Okay, 1, 2, 3, 4, 5. Each of the points where 2 sides meet is called a vertex. So if we have side BC and side DC, the common end point that they have is called the vertex. And then if you draw a segment between any 2 non-consecutive vertices, then you will get a diagonal. So if I go from D to A, that would be another diagonal. I cannot go from D to E because D and E are consecutive. I could go from A to C, and that would be another diagonal. So diagonal is the connection between 2 non-consecutive vertices. Okay, we're going to name polygons based on the number of sides that they have. So for the first few, you'll probably be extremely familiar with how you name those polygons. And for the first one, when it has 3 sides, you already know that that is called a triangle. I always want to call it a trilateral because lateral means 3 sides, or lateral means side. So I want to say trilateral, 3 sides, but we'll call it a triangle because it also has 3 angles. For a 4-sided figure, you call that a quadrilateral. For a 5-sided figure, we actually start using the gon here, and we call that a pentagon. 6-sided is a hexagon. 7-sided, heptagon. 8-sided, octagon. 9-sided, nonagon. 10-sided, decagon. 11-sided, I can't even remember the name of the 11-sided. Oh, this one is a dodecagon. And then when they have n, we just say an n-gon. I am going to have to look up what we call an 11-sided polygon because for some reason it is escaping me at the moment. Well, you can look it up too and bring it to class tomorrow and tell me what an 11-gon is called. Okay, so tell whether each figure is a polygon. If it is a polygon, name it by the number of sides. So remember, a polygon's formed by line segments. This is the closed plane figure formed by line segments, meaning at the vertices. And so I'm going to say, yeah, it definitely is a polygon, and it has 1, 2, 3, 4, 5, 6 sides. So that makes it a hexagon. Here's another closed plane figure that is made up of line segments. So we got 1, 2, 3, 4, 5, 6, 7. So this is a heptagon. And this is not a polygon because it is not made up of line segments. It has a curve here. So it's not even a polygon, so we cannot name it. Okay, now we have special kinds of polygons that we can take a look at, and here we want to look at what we call a regular polygon, a regular polygon. So when you see this word regular, it just means that all sides in the polygon are congruent. And not only are all the sides congruent, but in a polygon, if it's considered regular, all of the angles are also congruent to one another in a regular polygon. So those are the characteristics of a regular polygon. So you can see here an equilateral triangle is a regular polygon, a square, all sides and angles congruent, and then there are images of regular heptagons, nonagons, decagons, hexagons, and so on and so forth. Okay, so every single side in this figure, that's congruent to that, it's congruent to that, congruent to that, that, and that. And every single angle, that's congruent to that, it's congruent to that, it's congruent to that, it's congruent to that, that, and that. You can do that for every single figure. Okay, now we also have this idea or this concept of convex or concave polygons. So for a convex polygon, that means that all diagonals would be inside the polygon or on the interior of the polygon. Okay? If it's concave, a diagonal, exists on the exterior of the polygon. For me, I usually remember concave means it caves in. So if I were to take one of these polygons, I'm going to choose this guy here, and I were to draw all of the diagonals. That diagonal's on the interior, that diagonal's on the interior, that diagonal's on the interior, and that is on the interior. So this guy right here would be convex. Whereas if we were to take this guy, this diagonal is on the inside of the polygon, this diagonal is on the inside of the polygon, but this diagonal right here, diagonal on the outside, it's not in the inside. Diagonal, and I want to do that diagonal in a different color actually to make it stand out a little bit more. That's not bright enough. I like bright colors. So let's do it in this red here. There we go. So that's a diagonal, and it's on the exterior of this particular polygon. So because it's on the exterior, on the outside of our original polygon, this guy is concave. So we can go through really quickly and write convex or concave for each of these. You could try it first and then pause it and then look at the answers later. So this very first one right here would be convex, 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 concave, and concave. Okay? Alright, so let's classify these polygons now. First, we have to tell whether they're regular or irregular, and then following that, we have to tell whether they're convex or concave. This guy here has all four sides congruent, but all four angles are not congruent, so it's not regular. Therefore, we're going to label it irregular. And if I were to draw the diagonals, they would exist solely on the interior of the figure, so this guy is convex. The second one here, all of the angles are congruent, but all of the sides are definitely not congruent, so it is also irregular. And if I were to try to draw a diagonal, let's say from here to here, we can see that that exists on the outside of the figure. So it is concave. Here we have all four sides congruent, all four angles congruent, and the diagonals exist solely on the interior of the figure. So not only is it regular because of the all four sides and also all four angles being congruent, it is also convex. So we've classified those polygons as well. Okay, we can explore the sum of the interior of an angles of a polygon by using what we know about triangles. So if we were going to measure the sum of the angles of this triangle, we already know that one triangle, we see one triangle here, and the sum of the angles in a triangle, because of the triangle sum theorem, is 180 degrees. Now if we wanted to know the sum of all of these exterior angles of this quadrilateral here, this four-sided figure, we could find them by drawing in a diagonal here to create two triangles. And we know that each of these triangles has 180 degrees. So if we have a quadrilateral with four sides, the number of triangles that we would create would be two triangles. And then if each of them has 180, the sum of the interior angles would be 2 times 180, or 360 degrees. For a pentagon here, it has 5 sides. We can draw in 2 diagonals, which creates 3 triangles, 1, 2, 3. And then the sum of the sides would be 180 times 3, which would be 540 degrees. And for a 6-sided figure, we can draw 1, 2, 3 diagonals, forming 1, 2, 3, 4 triangles. And then the sum of the interior angles of all of those triangles would be 4 times 180, which would be 720 degrees. So if we were to go back here and put this 1 in, because it's 1 times 180, we could find a pattern. 3 sides, 1 times 180, 4 sides, 2 times 180, 5 sides, 3 times 180, 6 sides, 4 times 180. So it looks like we're always going to be multiplying something times 180 to get our final. Well, 4 is 2 less than 6, 3 is 2 less than 5, 2 is 2 less than 4, and 1 is 2 less than 3. So it looks like if we take the number of sides in and we subtract 2, we will end up with the measure of the sum of the interior angles of the triangle. So this right here would be n minus 2. So n minus 2 times 180 would be the total sum of the interior angles of any polygon. And that's just expressed right here. The sum of the interior angle measures of a convex polygon, I should have said that on the previous slide, with n sides is n minus 2 times 180. So let's use that information to solve a couple of problems here. So it says find the sum of the interior angle measures of a convex heptagon. Well, how many sides does a heptagon have? A heptagon is a 7-sided figure. So to find the sum of the interior angle measures of the heptagon, we're going to use n minus 2 times 180, where n this time is 7. So 7 minus 2 times 180, I'm going to bring my calculation up here, which is 5 times 180, which turns out to be 900 degrees. So if it is a convex heptagon, all of the interior angles will add up to 900 degrees. For this next one, it says find the measures of the interior angles of each, that's important, interior angle of a regular decagon. So a decagon, we first have to recall, is 10-sided, So they also said it's a regular decagon, which means that all 10 angles would be the same. So I'm going to use the sum again and do n minus 2 times 180, and that would be 10 minus 2 times 180, and take it up here, would be 8 times 180. So that would give us a total of 1,440 degrees for for all of the angles. This is the total for all 10 angles. But if it's regular, then that means that each of the angle measures have to be the same, and there's 10 of them. So that means if we just divide that by 10, each angle is 144 degrees. So you have to be sure that you're finding the correct thing. Are you finding the sum, or are you finding each individual angle? And you can only find each individual angle if they tell you that the figure is regular. Okay, find the measure of each interior angle of a pentagon ABCDE. Actually, here is one. They didn't tell you that it was regular, but they did give you a representation for every single angle. We've got 18C, 32C, 32C, 18C, and 35C. So we could find each angle in a figure like this. But first, we've got to figure out what they add up to. So this is a 1, 2, 3, 4, 5-sided figure. So if I do my n minus 2 times 180, I do 5 minus 2 times 180. That would be 3 times 180, which I believe is 540 degrees. So all of those angles have to add up to 540 degrees. That's the sum. So I have two 18Cs, I have two 32Cs, and I have one 35C. And if I add all of those up, they need to sum to 540. So we would get 36C plus 64C plus 35C equals 540. And then we got 36 plus 64 plus 35, and that gives us 135C equals 540. So if we divide both sides by 135, 540 divided by 135, we end up with C is equal to 4. So if I'm going to find the measure of each angle, we've got angle A, which is 35 times 4, so two of those is 70, which equals 140 degrees. Angle B is equal to angle E, and those are both 18 times 4. So 2 times that's 36, 72, which is equal to 72 degrees. And then angle C is equal to angle D, and those are both 32 times 4. So that would be 64, that would be 128, I believe. And so yes, both of those would be 128 degrees. So here's the measure of every angle in that convex polygon. Okay, we can also say something about the exterior angles of a polygon. And it says the sum of the exterior angles of a polygon always add up to 360. So let's take a four-sided figure here just to illustrate what the exterior angles are that we're referring to. So let's say we have this figure A, B, C, D. We know that the interior angles are going to add up to 360, but the exterior angles are when you take the side and you extend it. We did exterior angle of a triangle, but not of a polygon. So if you extend all those sides, we've got an exterior angle here. We got another one here. We got another one here. and another one there. So all of those exterior angles, the exterior angles are formed between an extended side and an original side. Extended side original, extended original, extended original. So we've got 4 exterior angles, and the sum of all 4 of those angles is going to be 360, and that's no matter what kind of polygon you have. Every single convex polygon, the exterior angles sum to 360. So if we look at this particular example, it says find the measure of each exterior angle of a regular dodecagon. A regular dodecagon would mean that it would be 12-sided, and it says of each exterior angle, so that means they're all the same because it is regular. So it's 12-sided, so it's going to have 12 exterior angles. Well, the sum of the exterior angles is 360, and there's 12 exterior angles, and they're all congruent because it is a regular figure. So if I do 360 divided by 12, I end up with each of those exterior angles being 30 degrees. Here it says find the measure of the value of B, and in this polygon FGHJKL. So you can see they've given us all of the exterior angle measures in this polygon, and we know that the sum of the exterior angles in any convex polygon will add up to 360. So we've got 33B plus 16B plus 10B plus 28B plus 15B plus 18B. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep, we got them all, and they have to equal 360. So I'm going to do 33 plus 16 plus 10 plus 28 plus 15 plus 18. Oh, and I missed a number. 33 plus 16 plus 10 plus 28 plus 15 plus 18. All right, so we get 120B is equal to 360, and then of course if we divide both sides by 120, we get the value of B is equal to 3, and that's what we were commissioned to find. It said find the value of B.